So the theorem can be used in reverse. So I hope you are convinced as far as at least group G is concerned, not the generic regular representation, but so long as these are elements that represent a group. So for that set it is true that they have to be broken up into cycles of equal length. Okay. So the theorem can be used in reverse. To represent, to discover group multiplication tables of a given size. So simplest example, if n is a prime number, then you cannot subdivide it into groups of equal length, because you can't subdivide it into any, it doesn't have any divisor. So if n is prime, then one can only have cycles of size n. Length, I think they are called lengths. Okay. So there is only one way of writing out, and you will have only one possible group. Because, well, I am asserting this without proving, but it is easy to see why. Because you will have to keep changing to represent. So if you can have cycle only of size n, and you have to have n elements, and you have to change, then the only way you can do is get only one group out of it. You cannot get two groups out of doing this. Furthermore, therefore, it is also easy to see that this will be nothing but the abelian group Cn. It will be just the n-fold, nth root of unity. So that is quite interesting and satisfying that after all this fancy thing we have some specific. The group has to be just the cyclic group of, that was the word I was trying to remember, cyclic group of size n. Next you can see example 2, although it is a bit simple again. We can check that C4 and Klein group are the only groups of order 4. Because we already checked that C4 has this thing 1, 2, 3, 4 and then some split 2 cycles and then again another cycle form, and of course identity is identity. So E equal to something, but these split into 2 elements of size 4 and 1 element which is 2 cycles. The client group is, as we claimed, breaking up into 3 2 cycles and the identity. There is no other way of dividing 4. Okay. There is no other way of partitioning 4. So this exhausts all the groups that you can possibly get at level 4 of size 4. Maybe I should fill in, but just to save time, you can fill in these, okay. So this exhausts kind of cycles you can make. There is a little more that needs to be said to make this watertight, which is, so why don't I have 2 elements with 2 cycles and then 2 elements with 4 cycles. See, here we had 3 elements which were essentially 4 cycle and only 1 element a 2 cycle. Here we got all 3 of them 2 cycle. Is it possible to have 3 elements of in a 4 cycle and 1 in a 2 cycle? The answer is no, okay, that you have to check. But that has to do with equivalence classes. The fact that equivalence classes retain the size. So I will just say it is incomplete proof right now, but intuitively this is clear. We will see the detail another time when we are doing something else, okay. So thus there are only, so we can check three 4 cycles and 1 pair of 2 cycles does not work. So hence there are only 2 such groups. Okay, so now it's 12 o'clock and there are 2, so I said we want to do 3 things, out of which 1 I have completed, but it has taken a little longer than I thought. And the 3 things consisted of doing this, then this theorem, this observations that we are making can actually be generalized and made much more interesting, okay. And so there is a theorem that one can prove, so I am launching it into it. We will see how we cover all the 3 parts, okay. So and generalization comes from introducing particular ways of writing out cycles. This can be generalized to this kind of process. To larger size groups without having to write out all the possible cycle structures explicitly, by a theorem that says that the number of ways of partitioning is what gives the possible number of groups you can have. So by introducing a concept of partitions, well, partitions for a number is clear. So we introduce this notation for cycles. So, given a pi which has nu k cycles of size k, so what we mean is, suppose I have a cycle of size k and I will keep counting how many these are, and this list is nu k, and then there are other things. I will do half of it now and then half of it next time. I will tell you the main result. What we do is we introduce lambda k equal to sum from starting from k and going up to total number n of nu k. So, note that the largest k is of course n. The size of longest cycle is the order of the group. So, the sum in k can go only up to n, but the trick we are doing is starting with some k and going up to n. Okay. You will see the advantage of doing this. So, thus we find lambda k minus lambda k minus, so lambda k plus 1 minus lambda k will be equal to nu k, because k plus 1 is a summation that will start with k plus 1. Sorry, so there should be a minus sign, right. So, one way of remembering this is, let us write like this, k plus 1 . So, the lambda k starts with k, lambda k plus 1 starts with k plus 1. So, nu k is equal to lambda k minus lambda k plus 1. Okay. So, if I write lambdas or I write nu, the description is equivalent. Okay. Whether I write the how many how many cycles of size k occur and remember the nu k's, or construct out of them the differences. So, what we have actually done is we can think of it also like this, that there is lambda 1 will be equal to nu 1 plus nu 2 up to nu n, right. Lambda 2 will start with nu 2 and go up to nu n, like this. So, this is what it is, and therefore, the difference of lambda 1 minus 2 will be simply equal to nu 1. We will start with nu k plus 1 and go up to nu n. So, the difference of lambda k minus lambda k plus 1 is simply nu k. So, there is a both lambda k and nu k are equivalent ways of writing out the cycle structure of how should we say, capturing the cycle structure, because the conversion is unique, right? This it's a linear relation between, okay. So now the advantage of writing in terms of lambdas is now the following. If I sum all the lambdas, I get back n. Okay. Why is that true? Well, look at this explicit way that we wrote out this. If I start summing the lambdas, I will get nu 1 exactly once, I will get nu 2 exactly twice. So in other words, is actually equal to, so as we saw, nu 2 will occur twice, in this sum nu 3 will occur thrice, so actually it amounts to k times nu k. The cycle of size nu k will occur exactly k times in this sum of the lambdas, but that has to reproduce the total thing n. If I count the number of ways that cycle, kth cycle occurs, the sum of all the lengths, sum of all, this is actually sum of all the cycles. Okay. Equal to number of total elements in all cycles. So it exhausts all the elements, which is equal to n. So this means that so now one can establish a relationship between the kind of cycle structures one can have and the order of the group. So thus we have is equal to the number of ways of partitioning n. Because you write out what is meant by partitions, n equal to lambda 1 plus lambda 2 etc. What did we write? Yeah, up to lambda n. Try to partition it in all possible ways. So some of the lambdas can be 0. Note many nus can be 0 and many lambda k can be 0. When successive k's have same number of cycles and nu k is same for k and k plus 1, then the difference is 0. Okay, so I want to leave this theorem here right now, because I think some of the things we need to go over again before we capture all the essence of this theorem. So for the time being, I will just leave you with this enumeration and summation exercise, and we will see later what is the further significance of this in trying to determine structures of groups as a general thing. So with this, we finished these two parts of today's lecture. What I am going to do next is symmetry notations in chemistry, molecular symmetry. So it turns out that one can capture all the possibilities in a small list. So let me begin by saying the elements of symmetry operations. And then there is kinds of groups. The elements of symmetry operation are things like rotation, reflection, and so on. And what combination of rotations and a few reflections makes up a set, a group, is there are notations for that. So elements of symmetry groups are, as we saw, first n-fold axis, which we usually represent by z-axis. And so let me see if I can switch between this and this. So let me first write this list here and then we will see the simple example. So n-fold axis of rotation, then there is something called sigma v. This is a reflection plane which contains this vertical axis itself. Okay, so think of water molecule, and I can draw a vertical axis which switches the two hydrogens, that reflection. So there is a reflection plane containing the symmetry axis, but there can be another kind of reflection plane which is called sigma h, and this is a reflection plane perpendicular to the rotation axis. Then other kind of transformations are having a sigma 2 axis, sorry, a C2 axis perpendicular to the n-fold axis. So you think of molecule which has, I think I should show pictures. So I have an axis of rotation, but I have perpendicular axis which flips things in such a way. So I see two axis only, just pi rotations which are perpendicular to it, which also keep it invariant. So take a square. So you can have a fourfold axis of rotation, but you can have axes passing through the diagonals and axes bisecting the square, around which you can do 180 degree rotations. So those are C2 axes perpendicular to the n-fold symmetry, n-fold rotation axis. And then there is a nomenclature for the groups. So, let us look at some examples. So, take note of this place, university called Otterbein. It is in Ohio, I think, and they are maintaining a complete kind of tutorial of symmetry as far as used in chemistry. So, this is the water molecule and it has a sigma 2 axis. So, it passes through and so z axis is pointing towards us. It has two planes which are both actually sigma v. In the notation I just said, one plane passes like this. So, one is x z in which you can reflect, or there is a y z which does not do much, right, because it is just passing like this and it is a planar molecule. So, every planar molecule always has a plane which trivially reflects it into itself. Let us look at benzene. Okay, so this has all kinds of elements, and I did not so far say about inversion, so we will see everything here. So, first of all, it has, of course, as you know famously, the 6-fold axis. So, it rotates once, well, it shows only the first element. Okay. Then of course, there is a C3 axis which is just going to do this, it is a combination element. Okay. C2 axis which is pi rotation. I do not know what C2 prime is. So, this is my C2 axis, as I said in last thing I said, the C2 axis which is supposed to actually be perpendicular. So, this C6 axis is pointing into the plane of the picture, whereas this C2 prime is perpendicular to it. And there are of course 3 C2 primes, as you may imagine, one in each of these, the third one is there, and then there are C2 double prime. So, there are 3 C2 axes which pass through the molecule, through the atoms, and another 3 which dihedrally cut the bonds. So, this C6, C3 and C2 are only elements of the cyclic group C6, but these primed axes are the ones that are cutting the bonds into half. Okay. Other than that, there are all these sigma v planes. Okay. There is sigma v1, sigma v2, sigma v3. Sigma v means a plane that contains the n-fold axis of rotation. So, one of them, so our axis of rotation is z and is coming out of the plane of this screen. Sigma y does this reflection, sigma, another sigma which will do this. So, these sigma planes are all passing through these, and there is another category of sigma which are called sigma d. So, the sigma d are called dihedral planes. Dihedral because they take the, so instinctively these are the simpler planes, right. So, let me remove this. The ones that pass through the atoms are the important planes to consider. Additionally, there is a plane which divides two of those. So, these two orange planes are divided by this yellow plane. So, the plane that falls in between two of those category of planes is called a dihedral plane. So, it is called sigma d, and does it do something? Okay, well, so that reflected around that plane. So, this is the whole list, and finally, there is the very simple sigma h plane which is passing through this planar molecule. And if I reflect, let us see what they show. not much. Okay. So because it's just anyway you cannot distinguish upper part of carbon molecule for lower part, but there is that sigma h. So this introduces all the notations, the sigma v, the sigma h, and the sigma 2 primes. Whenever they say sigma 2 primes, it means that they are flip 180 degree rotation axis perpendicular to the main symmetry axis of rotation. So ethane, okay. Oh, and the groups are written here. So sigma water is essentially called, so that was the other part I was going to introduce, which is the list of the groups that you get eventually. So the sigma and C2 primes etc. are elements of the symmetries, CN symmetry, but finally we have nomenclatures for groups. So this is called C2V because it is, firstly it is C2 because it has this C2 axis of rotation and it has vertical planes of symmetry. I was looking for whether the ammonia molecule. No. So, oh well, methane. So there are also elements like methane which are extremely symmetric because they have extremely large extent of symmetry. They just 4 carbons. Here you have to imagine these 2 carbons as coming out of the plane and these 2 bonds going into the plane, and it has 24 symmetry elements. But essentially generated by fewer ones. So essentially there is a reflection plane of this type which contains 2 of the carbons at a time, hydrogens at a time, and it has C3 axis which is an interesting axis. It passes through this and through one of the hydrogens. So if you rotate, it rotates like this. But then of course you can do this with any of this hydrogens, right. So there are 4 such C3 axes, and then there are interesting C2 axes which are not intuitively clear at first. Okay. So this goes through this, and if I rotate this all the way around, you get here, and right, you can see it here. And then there is an S4 axis. So that is another symbol S. So when they use S, it means a rotation followed by a reflection in the perpendicular plane. So it is an improper rotation. We will do again next time, we will start with all this. So the S4 axes are basically a 90 degree rotation followed, so they are trying to probably show it. The rotation axis is going to be this, and then there is going to be a reflection in this. Okay. So note it first, it is going to reflect in this plane afterward, the thick plane. It is going to first rotate by 180 degrees there, and then it flips it, okay, then it comes back. So this has much larger group, and they have here shown individually also what is meant by reflection, okay, sigma, but there is no, here ammonia. Ammonia is a good molecule to have. Okay, does it do anything? No. Okay, so proper rotations and improper rotations. So it will show all of this. Improper through methane, we already saw, well, ethane. We saw methane, but the case of ethane will also have S6 axis. Right, so what is happening? You see what is happening, they are rotating this up to here, which is 2 pi by 6 rotation and then reflecting it in the green plane, then you get back the molecule. So last part is the reflection. So this is called an S kind of axis, a rotation and a reflection. Okay, so we'll see more about this next time.